Hello class, this is Adam Ward, and we're going to take a look at major losses under laminar flow conditions today, specifically applying the Hagen-Poiseulle equation. Here's an exercise that we're given with oil flowing from top to bottom through a vertical pipe. We're asked to find what the manometer reading will be in this problem, which is representing that pressure drop from point 1 to point 2. And so as a starting point, we'll go back to hydrostatics, and we can write down the manometer equation relating points 1 and 2. Now, from the diagram, we can relate a couple of these dimensions to one another. So two relationships that link the different h values and the overall L that we're given of 4 meters between the 2 points. And we can also express this as a pressure drop, or delta P, by setting that equal to P1 minus P2. And so with those updates, we end up with an equation that looks something like this. We have information about the fluid properties here, so we're given specific gravities. We can calculate specific gravity both for the oil and for the manometer fluid. And so that leaves us at a point where we've got one equation but two unknowns. We don't know the pressure drop and we don't know the manometer reading. Fortunately for us, we do have another equation we can bring to bear on the problem, the Hagen-Poiseulle equation, which I'm writing on the right-hand side of the slide now. This Hagen-Poiseulle equation describes discharge as a function of pressure drop, pipe geometry, the direction of flow, and so forth. And remember, this applies only for conditions of laminar flow. And so we're going to go ahead and check if that flow is indeed laminar. You can see that we're also going to need mu. So I've gone ahead and calculated mu on the bottom left down in our fluid properties section. As we verify if it's indeed laminar, we'll look at the Reynolds number. And we want to find a Reynolds number of less than 2100 to indicate that it's laminar flow. To calculate Reynolds number, we'll need velocity. So in the bottom left, I'm using Q over A to calculate velocity of 1.27 meters per second. Now we can combine these values into a Reynolds number of 115. So the problem is indeed laminar, and we can move forward. For our Hagen-Poiseulle equation, one thing we want to note here, the sine theta term that has to do with the direction, where theta of 0 would be horizontal flow from left to right. And so you can imagine that this is an angle of either negative 90 degrees or positive 270 degrees. And so the sine of that becomes negative 1. We can simplify the Hagen-Poiseulle equation and rearrange it for pressure drop. Take that equation, use that for the left-hand side and the right-hand side from the manometer equation now. We can cancel a few terms. And from this equation, we've now got one equation with one unknown, h. So we'll go ahead and plug in all of the numerical values that we've calculated for fluid properties and the geometry of the project, or the problem, excuse me. And I come up with a solution of 18.5 meters for the measurement h. I hope you found this useful and see how the Hagen-Poiseulle equation can be combined with hydrostatics in order to apply to certain problems. Thank you.